When you're ready, Mari-Carmen.
Okay. Okay, so yeah, to like recapitulate a bit. So in the first part, I sort of gave you the generality of tensor states, and then I was describing all the properties we know about matrix product states, so the main ones. And I will now just mention the last one, which is I promised to do it before, and it's like this generalization of the AKLT construction. Which is also a very important property because it basically tells us that matrix product states, with some considerations or with some conditions, they are ground states of local Hamiltonians. And in so in these special conditions, they are unique ones. So this is a very powerful tool to construct exactly solvable models, because you can construct the ground state, and then from the ground state you can construct the Hamiltonian. And you know already some properties it has. And this is this parent Hamiltonian construction. Then I will move on to the generalization to higher dimensions, which is PEPs. And I will present what they are, give some examples, and go over the properties, mostly over the same properties I mentioned in here, to make special emphasis on the differences. So what is different for PEPs and for MPs. And then I move to the algorithms, like what kind of things you can do with them. And I think that I will have to stop because we won't have time for more. But in the last few minutes, I'll probably mention the couple of other things that one could look at or study to get a more general picture of what people are doing now with this tensor network stuff. So the parent Hamiltonian construction, as I said, is this generalization of the AKLT one. So the AKLT model, if you remember, was this first matrix product state that was introduced actually to have a state that by construction is the ground state of a local Hamiltonian, spin Hamiltonian. So here the state is an MPS, and the question is, when is this MPS the ground state of a Hamiltonian certain property? So a key ingredient to be able to prove these things is this injectivity property. So this injectivity property, which appears often in these results, means when we take one tensor of the MPS, it has three indices, right? Two virtual ones, so D times D, and then one physical one. So it can be understood as a map of the virtual space onto the physical one, right? How does this map act? Well, you apply this to some matrix in the D times D space and obtain some vector in the physical space, right? So applying this to a matrix would be to plug in here some x, and you would obtain something which is a vector in the physical space, right? And somehow, depending on the tensors that you plug in, you will be able to generate some vectors, and some others will never appear here. Okay? And well, injectivity means that this kind of map is injective. It means that for any matrix X that you put in here, you get a different vector. Or only for 0, you get 0. It's the same thing. And if you look at an MPS, again, injectivity is something that happens for most MPSs that you can construct. Not for a single tensor, but see what happens with MPSs. So if you take one tensor, and instead of one tensor, you now take two sides, you can now construct a bigger tensor for two sides, so construct an effective side which corresponds to two sides, and the physical dimension increases now, it's the square, but the virtual dimension is still the same. And you can continue doing this, and then you will have something which is d to the n, while here is still d times d. So, because this grows exponentially, but this doesn't grow, at some point, this space is so much larger than this one, that injectivity is the generic property, right? You won't hit twice the same element there. You just pick up d times d. So you can do it, but it won't be the generic thing. It will be for specially tailored tensors. So this is injectivity. And so you can just think of one tensor, because if it doesn't happen for one, say you just block enough of them and take this and call this your sign, a single sign. So saying that a tensor is injective is the same thing as saying that there is a left inverse, which means that there is another tensor, A minus 1, such that when you do this contraction, this gives you the identity. And this is the identity on the virtual space, right? And, okay, here is where I wanted to mention this canonical form, something that I just jumped over last time. So the canonical form is such that there could be more than one block in the tensor, right? So when you take your A tensors, so they can have a block structure, say A1, A2, and so on. So for an injective tensor, whatever number, P. So for an injective tensor, what happens is that the canonical form has just one block. It also means that if you would just act on the physical indices, you can access all the virtual elements in here. Or somehow that this matrix here, or products of these matrices somehow generate the whole space of virtual, the virtual degrees of freedom, the D times D matrices. If it has a block structure, this is not true because you will have zeros here. No matter how many of these guys you take together, you will still have zeros in these blocks where you have zeros. So this injectivity is the same thing as saying that in the canonical form you have just one block in the matrices, and in the non-injective case you don't have anything arbitrarily, you still have a canonical form which has several blocks. And in each of these several blocks, you might have one of these eigenvalue 1 for the transfer operator. This is the connection to the things that we were discussing just before. This is just a note aside because it connects to what I was saying before. Okay, so if you have an injective Hamiltonian, okay, this is just a way of seeing the same thing, but it's just something that you need for the proof, but I'm not showing the proof here. I'm just telling you how you construct the parent Hamiltonian. So you have this tensor, which is injective, and then you take two of them, and this is just because then you can take like nearest neighbor terms in terms of these sides, whatever they are, they might be blocks of sides, but two of them, and cover the whole system. Then you have a nearest neighbor Hamiltonian, and it's constructed from two tensors like this. And say that you construct all the vectors on two sides that you obtain by plugging a matrix on the virtual space for two tensors, right? And we call this S2. And X is some complex matrix in D times D dimension, whatever, right? This is sort of whatever two-side states you can generate with these tensors, right? There's nothing more. And now, say that you take the projector onto the orthogonal space to this one, right? Where I just call it this way, right? For side I and I plus 1. And I sum over all sides I. And this is what I call Hamiltonian here. So over all the system size, right? So, so this Hamiltonian is actually the parent Hamiltonian of the ground of the state given by that, right? So the state would be, in this case, a collection of all the same tensors, A, right? And I'm just projecting over the orthogonal of whatever I can generate with these states, right? So this state will give 0. Right? So it's a sum of projectors, and it gives 0 over the states that I have, the state that I have. So it's certainly a ground state, because it's a positive thing, it's a sum of projectors, and the eigenvalue is 0. And you can show that it is actually the only ground state by using this injective property, but this gets a bit more, it's actually a nice proof. It can be seen in a paper by Norbert Such from 2010. I can look for the exact reference if somebody is interested. It's very nice because you can prove it with these just graphical pictures. It's very intuitive to see how this is true. But the main thing that I want to say here is that, okay, this is known. If you have an LPS and it has a generic property, then you know how to construct a local Hamiltonian, and it will be the unique state. So you have a gap Hamiltonian which has this ground state. And actually you can also look at cases where there are some symmetries and it's not. Then there is a degeneracy, and this is connected to topology. And so there are many more things that you can do with this, but I'm not entering into these details. This is the basic of the construction. You can just see that the generalization of the AKLT construction. And so if there are there any questions about the MPS system? Yes?
Yeah, I would like to maybe to talk about more specific cases. There you wrote the S. For example, if the interaction is okay, mu is neighbor, but the spins are vectors or scalar numbers. Imagine that the interaction is S1, S2, but where S are numbers, or.
But this is a classical Hamiltonian. I don't know what you mean. S1, S2. So this is a generic construction for an MPS. So I give you an MPS. I didn't tell you that it has to be qubits or anything, that the one dimension, so that the physical dimension has to be 2. And actually, this A here could just come from blocking together some number of sites, so that the whole thing is that the site is injected, the tensor for this effective site is injected. It's not a spin, but this is a nearest neighbor construction in these sites, right? In terms of these sites. And it has to be nearest neighbor, so actually you could do just a projection on one side, and it would be a ground state, because you cannot generate anything outside of something like this, and so on. But then you wouldn't be able to prove that it is unique. So to prove that it's unique, you do this construction, and then you have a local Hamiltonian for which it is a ground state. And it's completely general just from the injectivity of the MPS. It doesn't rely on any particular dimension. So also the small d, this is what you are thinking about, this small d can be, it's finite of course, but it can be as large as it requires to be for it to be injective.
Yeah, I understand it's not spin or half or...
No, not at all. I mean, it's just a generalization. That's why it is a generalization, right? Because it's, you give these tensors, and whatever they are, if they are injective, you have this construction that works, and it has a unique ground state, which is of this one. Okay. Yeah, I didn't show you the slides, I was telling this, but okay, here is the same thing. And actually, when I wrote here that this is also true for PEPs, I will tell you in a minute again, because now I would like to move to the generalization to higher dimensions, which is PEPs. So one of the nice things of this construction that I showed you before, with the quantum information form of producing mixed web states, so putting these maximally entangled pairs along each link of the lattice. So I told you before, we had a one-dimensional lattice, and we put these maximally entangled pairs across each, so along each link, and then we would do this local projection, right? But of course, there is, in this construction, there is nothing against doing it on a different lattice. So you could think of a two-dimensional regular lattice, like a square lattice, and then you would have also neighbors here, 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 and here, and here, and here. And you could do the same thing, so put these maximally entangled pairs along each link. And so on. So all of them. Of course, you can also make it periodic by connecting like this, but then the drawing gets very ugly, so I won't do it now. And then you can just map all the local virtual degrees of freedom to the local physical ones. Instead of a two-leg to one mapping as we had before, now it will be 4, right? So we will have some left and right and up and down pairs in general, like if you look at this side, right? So this would be left, right, up and down, for instance, with this orientation. And this guy, we will map to the physical states of the side, which could be a spin 1/2, it could be a qubit, it could be a spin 3/2, it could be something else with finite dimension. And this will have some coefficients that, well, in the first paper were called B's, I think. So I keep these B's here, but very often they are called A's also, because actually an MPS is only a PEPS, so it's just a particular case. I, left, right, up, down. And this would be your local projector, in this case, for a single side. So you have exactly the same construction, but now putting these maximally entangled pairs across every link, so along every link on the lattice. And of course, it's not restricted to a square, two-dimensional lattice. You can do this on any graph you want. So you can do it also on a three-dimensional lattice, you can do it on any planar graph or not planar graph or whatever. You just put one of these maximally entangled pairs across so along every link, and then project locally. And this gives you a tensor network for a particular geometry, so to say. Okay, I have a note here, which is Important to keep in mind. I told you before that matrix product states are completely general in the sense that they are a complete family. You can describe any state in the Hilbert space that you want with them. So you can also ask why worry about PEPs, so about doing some extra family. If anyway, even if your system is two-dimensional, you can still use one-dimensional answers. That's true. But the way you do and actually in practice you do it, and it's one of the most powerful ways to study numerically two-dimensional systems right now. But it has one problem, and it is that if you do the MPS, you have to sort of choose a one-dimensional ordering for your sites, because the MPS has an ordering of the matrices, right? And it doesn't matter, you just choose one. So imagine that you choose it like this, so like a snake, right? So you wrap an MPS passing through every site in your system. That's fine. You can describe any state you want like that. But how big is the one dimension you need to do that? Well, if this state has an area log, it means that when you truncate, for instance, here or here, right, the upper part with respect to the lower part, we will have an entanglement which is upper bounded by the size of the boundary, which is in this case the number of sites, right? So the one dimension you will need in here to describe this boundary sized entanglement, because the entropy in the MPS is upper bounded by the logarithm of the one dimension is exponential with the entropy, right? So the one dimension you will need will be exponential with the, say, horizontal size of this guy, the same if you do some other orientation. It means that it won't be efficient in this dimension. So you can still do precise numerical calculations. People do them using huge matrix product states to study interesting two-dimensional problems. But if you need to go a bit larger system to get meaningful results, it scales very poorly with the system size, the one dimension you need, and hence the computational costs. Okay. The MPS, the PEPS is a two-dimensional family which by construction satisfies the area law. And to see this, you just need to think of cutting out a part of the lattice and do exactly the same reasoning we did before for the one-dimensional case. How much entanglement you have between this part and the rest? You just need to count the number of maximally entangled pairs that you cut. And the number of maximally entangled pairs, they are living on the boundary. So it just looks like the boundary. So by construction, it has an area law. Okay, this is one of the motivations. Again, you can easily see that that it is a complete family. So you can actually use this construction. This is one PEPS, right? So it's a particular PEPS where not all the bond dimensions are the same. It has one bond dimension 1, and because we know that matrix product states are complete, well, of course, PEPs are complete because they contain matrix product states. You can also do the same kind of generic decomposition that we did before and say that by doing singular value decompositions, you will end up with some PEPs, but the one dimension you will require to describe an arbitrary state in the Hilbert space will still be exponentially large. Okay, just as we did for MPSs, some interesting quantum information states can be expressed exactly as pairs. And one example is the cluster state. So the cluster state was introduced by Briegel and Rausendorf in 2001, so already some years ago, and it was shown to be very powerful for quantum computation, right? Because it can be the basis for measurement-based quantum computation. So it's a state that has a lot of entanglement somehow, and it can be constructed. Well, it has a lot of entanglement or useful entanglement for quantum computation, if you want to be more precise. It can be constructed in this way. So you can just start with a product state where so you have some system. Say you have a two-dimensional lattice in this case. Okay, we consider a two-dimensional square lattice, and you prepare each subsystem in a superposition of 0 and 1, equal superposition. So this is what we call a plus state. Okay, I omit the normalizations here. And then we act with unitaries on neighboring pairs. Okay, so you have your two-dimensional lattice. So drawings get more complicated when you get to more costly when you get to 2 dimensions. So you have each side in a product, right, and so on. And then you start applying these unitaries on each pair in here. And these unitaries are some exponential of some phase which, okay, for the cluster state, what everybody calls cluster state of the time is fine, of this two-body operator, which is as 1 minus and 1 plus 1 minus. 1 plus sigma z divided by 2 on one spin, tensor 1 minus sigma z on the second spin. Right? The exponential of this thing. So it's a two-body operator. Okay. Yeah, I don't think it's so interesting to do the composition. You can easily see that you can just write the expansion of this exponential and end up in this form, right? So it means that this exponential can be written as a sum of two products of single body operators, like identity times identity plus something. It's like the exponential of sigma z, okay? Then that you can write identity tensor identity plus something sigma z tensor sigma z. Or if you think of the single sigma z, you can then go on. And the graphical way of showing this is this unitary is an operator on two sides. This is a tensor also that has two input indices and two output indices, right? And by using this decomposition, I can write it as a sum of just two products of local operators. This means I can write it as a sort of an MPS form, right? With one dimension only two, because there are only two terms, right? So if I just write the sum explicitly, is this more or less clear, this picture? Okay. So if I do this everywhere, I just have a PEPS form, right? Because on every side, I would have one side of this thing, either pointing left, or pointing right, or pointing, say, upwards, or pointing downwards, okay? And if I just take this thing together, and below, I just have one initial state, which was this plus, because this was in a product. There is no bond going out. And this is on every side. I can do this on every side and end up in the tensor for the PEPS. Okay, I didn't do this picture before. It's shown in there somewhere, not anymore. Okay, sometimes we draw the PEPS tensors in 3 dimensions to make all the indices clear, because we have like one dimension for the physical index and then the others live on the lattice. I mean, I don't write the explicit expressions. You could like play with them, but just by using this decomposition, it is clear that it has this form. For the d equal to, you really have to work this out. In general, any thing that is a two-side operator, like this, or on two spin 1/2 systems, we could just do a singular value decomposition here, and at most it will have 4 singular values. So in a generic case, we would have like a d equal for some state of this one. But okay, the cluster state is like especially interesting for the quantum information implications. Also, the ground state of the theory code has an PEPS description, but I'm just skipping that one because it's just another example. And let's look now at some properties which are really like different from the case of the MPS. So you look at this ansatz, the PEPS ansatz, and it's a very natural generalization of the MPS, and it would be very natural to us if all the properties of the MPS translate to the PEPS. But it turns out that some of the properties that I told you about of the MPS end up being quite different. So the PEPS family is much more complicated in a way. It contains many complicated states inside. It contains physical states, physical interesting states, but it contains also very complicated states. So the first thing is that completely different to what happens to MPSs, PEPs can have algebraically decaying correlations. If you take 2-point correlations, they can decay algebraically. So you might find this not so surprising because, of course, if you look at how many ways there are to go from one point to another one in a one-dimensional lattice, there is only one. So this thing is limited. In a two-dimensional lattice, there is much more. There are many more. But not all two-dimensional ansatz will have this property. But PEPs have this, and it's there is a very nice way to see it. And I thought I had written, I wrote the reference somewhere, but it's probably before. Well, it's in a paper by Frankfurt Strepe and co-workers in PRL in 2006. If you want to see the explicit construction, because I think I'm not doing the explicit calculation here, I'm just telling you how they did this. And the idea is very nice, is you can construct a state which is reproducing the properties of a classical partition function. So you take the two-dimensional Ising model, classical one. So the two-dimensional Ising model looks like this. It's a sum of nearest neighbor terms. So SS, you could think of sigma z, okay? But it's classical. Everything is diagonal in this. There is only +1, -1 values for these S's, and there's no sigma x involved. So it's just diagonal, okay? So the two-dimensional Ising model is known to be critical at a certain temperature. So there is an exact solution for this, and this temperature, I wrote it here, this is a logarithm here, and it's 0.44, whatever. The partition function of this thing is this sum over all configurations of all the spins of e to the minus beta, the value of the Hamiltonian for some configuration. So you can define a quantum state which has, for each possible element in the computational basis, which corresponds to a configuration of the spins, it has the weight, the corresponding weight in the partition function. Actually, you use the beta halves because at the end what you want is to compute expectation values, so you will have a sandwich and you will have beta halves. And you will have beta halves on each side, and then you normalize, of course. So if you compute correlations, these correlations will just give you the correlations in the corresponding thermal state of the classical Ising model, just by construction, because it's just it's a state designed to give you these correlations. Because this model is critical at that temperature, if you tune the beta to be the critical one, you will have critical correlations. So this model is known to have critical correlations or algebraically decaying correlations at this temperature. And now the only thing that you need to see is that this guy is actually a PEPS. And it is a PEPS with a very small one dimension. And to see this is very similar to what I just told you before. You just write this thing. Okay, this partition, so this coefficient of the partition function, of course, you can write as sigma sets acting on the computational basis, right? Because the S is just the eigenvalue of the sigma sets. Everything is diagonal in the sigma set, so instead of writing the value, you write the operator. And this is just a number of two-body terms which commute with each other, so you can break down the exponential as a product of exponentials. Exactly. And now you look at one of these exponentials, and you can write it exactly as a linear combination of, again, products of single-side operators, like the identity, and sigma set times sigma set. And we do exactly the same thing as before. So you have the D equal to the composition for one of these operators. Okay, here I just wrote it a bit strange in a different basis, but anyway, you can think of the extra index, and then you use the local terms to construct the single tensor. You have a PEPS with one dimension too, exactly as before. We have some different components, so it's exactly as before. And just by construction, at the right temperature, it will have algebraically decaying correlations, which go like that, 1 over the square root of R. Okay, so that's pretty different from the matrix product state properties. Another thing that is pretty different is the computation of expectation values. And that's sort of very relevant if you want to do anything in practice. As I said before, you really want to be able to compute expectation values of observables, maybe not all of them. I mean, if the operator is not local, I mean, if it is something which is completely global, then the operator itself is exponentially costly. And then it's no surprise that you won't be able to compute things even if your ansatz is efficient. But you want to be able to compute at least expectation values of local operators, correlation functions, and so on. So what is the difference in the two-dimensional case with respect to the one-dimensional? If you recall the argument, while in one dimension you can compute expectation values very efficiently, is that the expectation value is the contraction of, say, a bra, some local operator, and a k. You can think of the norm without any operator or anything, right? So it's a bra and a k. And instead of doing this contraction in an inefficient way by computing its coefficient in the computational basis, you can do it in an efficient way by contracting together the local tensors, and then you end up with a product of matrices, which can be done efficiently and doesn't depend on the system's. Okay, it depends on the system size because you have to do n calculations, right, at the end. But it's only linear on the system size. The cost doesn't increase exponentially with the system size. So what if you do the same thing with PEPs? Of course, you can do the same kind of construction, right? So you have your PEPs. Let me just do some simplified drawings for the PEPs, right, which looks like this. So I'm not drawing the boxes anymore. And then you want to contract, say, with its adjoint. No, too big. Sorry. Okay. So you just take the adjoint and connect the corresponding legs. This won't work. And so on, right? So you know the idea. So this is what you need to do to compute the norm of a PEPs. Okay? Now we look at it from above, right? So if you want, we say for each of these tensors, this is the equivalent to the transfer operator that we defined before. So we call this thing E now. Only it's an operator which has 4 indices, right? It's not a matrix. If you just keep the 4 indices, of course you can reshape it to a matrix by grouping them. But okay, now let's look at the thing from above. Well, from above, the thing will look like this. And then I draw 2 bonds everywhere. Meaning that each of these guys is like 2 layers. Okay? It's higher, it's bigger in dimension than it was before the PEPs, but it has n times n size. So why can't we do here the same trick that we did for the matrix product state? Well, now the goal is to contract this thing together. Right? This is a scalar, no open indices. How do we end up finding the scalar? You can start contracting things, right? You can take this guy, and this has like d squared times d squared, and then you contract it with this guy, and then it turns out that it has d squared times d squared times d squared, and so on. And when you have something like this, it will have d squared, say, to the L, if it was L times L. So you end up on something which is exponentially large in the system size. And no matter how you choose to do this contraction, if you want to keep the whole result, it grows exponentially with the system size. So it means that you cannot compute efficiently expectation values in PEPs. And actually, it was shown by Norbert Su that that is a very hard problem. If you are given an arbitrary PEPs and you would be able to contract it exactly, this will give you a lot of computational power. So the complexity of doing that is Sharpie. So, well, Sharpie complete actually, which is much more difficult than like NP complete. So NP complete is whether something, so okay, to be very roughly speaking, about some very difficult problem to say whether there is a solution or not. And this Sharpie is like telling how many solutions there are. So it's hard. So it just tells you that contracting PEPs in a generic case, right? So if it is an arbitrary case, it's very hard, so you are not going to be able to do it exactly. However, in practice, you can use some approximate contractions. And there are approximate contraction schemes which are efficient. So I will just tell you about one here. It's not the only one, there are other ways. The key will be whether these things approximate well the contraction that you want to calculate. And in many interesting physical cases, like cases that you use in practice, this is the case. But in some other cases, it won't be, okay? But, okay, what is the idea? Well, the idea is to use the kind of algorithm that we have for one-dimensional systems. So you can see this two-dimensional network that is going to contract now. You can just see it as, okay, this boundary has this structure, right? This is a structure that we already know. This is an LPS. I'm just putting one index for the double one, it doesn't really matter. So what we have to do is to contract it together with the next column. The next column has also this kind of MPS structure, only now it's an operator. This is what we call an MPO, matrix product operator. And if we want to contract it exactly, we have to take the product of dimensions. We are in the same problem as before, because at the end we will have something exponentially large. But what we can do is to approximate this thing by another MPS. And we have algorithms to do that. And we can estimate what the error of doing that is. So it means that we can go from one edge to the of the lattice to the other, contracting every time one column, and so keeping track of how big the error is. We can also do the contraction in the other direction to estimate how big our errors are. These are more details for the practical implementation. But at the end, it means that in practice, we still know how to use these approximate contraction schemes to run algorithms with the PEPs ansatz. Only everything gets much more costly than in the MPS. Okay, what else? Preparation of states, I'm just mentioning it because it's also very different from the one-dimensional case. So the matrix coexist can all be prepared efficiently in the lab if you would have a lab that can do any unitary on your sites, say, because you have a sequential operations. You do an operation on a few sites and you displace them one and you do an operation and so on. This is not possible on PEPs. Okay, on some PEPs it works. So there are subfamilies of PEPs for which this is true, but not for a generic PEPs. And it's actually a very hard problem to prepare a generic PEPs. This has also been proven. So there is also apparent Hamiltonian construction. Okay. Yes. So there is also apparent Hamiltonian construction, which is actually basically the same one as for MPS. It generalizes directly. So the same kind of construction that I did for MPSs, you can do for PEPs, only, well, you will have, like, say, 2 times 2 region, and then the boundary is larger because it has, like, bonds going also to the front and to the back. But you do exactly the same kind of projector, and you can construct a Hamiltonian which is local, and if the PEPs has some injectivity property, then you will have that you have a ground, so you have a local Hamiltonian for which the PEPs is a ground state, and it is unique. Yeah, it's basically the same construction, so it's actually, yeah, very nice. The difference with MPSs is that in the MPS case, this injective implies unique ground state goes in both directions. In the PEPs goes this direction. Injective implies unique ground state only. This is maybe, yeah. Yes.
For example, the excited states of these parent Hamiltonians, you can say something about this from the ground state. You can evaluate properties of this excited or you only.
Okay. There is something you can say in many cases. So from the properties of the transfer operator, you can say things about excited states. So if you are given an MPS, or yeah, I guess PEPs also, I'm not sure about the PEPs, for an MPS for sure, you can look at the spectral properties of the transfer operator, and it contains information about the low energy excitations. But I don't know if this is connected to the parent Hamiltonian construction. I should check it out. Then there is another thing which is changing the tensor and seeing how the parent Hamiltonian changes and how the gap changes. But this is a different issue. But so in the generic case, I don't know, but I could, yeah, I should check. So I mean about the connection to the parent Hamiltonian. But in general, if you have an MPS, which is ground state of some theories, yeah, when excitations can be described locally, yeah, then you have information in the transfer operator, which is contained in the ground state itself. So somehow, yes, you would expect that it's also in the parent Hamiltonian somehow, but I don't know exactly how. Right? So both of them come from the tensor. So I'm just skipping this, although it's a very interesting line of research now, which is that PEPs, I'm just mentioning it because I think otherwise, yeah, I will just show this. Yeah. There is a very nice connection with some holography principles. This is not the relation to the general relativity models that you will hear about when you hear about MERA in the conference probably, because students won't have time. But it's a very nice relation, the kind of relation that has been explored for fractional quantum Hall effect models, where people have looked at the entanglement spectrum and seen how when you look at the radiation density matrix for a piece of the bulk of the material of the system, then you can define a Hamiltonian, which comes from the radiation density matrix from the bulk, which contains or resembles the Hamiltonian of a one-dimensional theory. So there is some mapping between a one-dimensional critical theory and the bulk, so which is a two-dimensional system, given by the ground state of this thing. Well, the PEPs just realize this naturally. So when you have a PEPs, you have this connection. And this has also been used, I won't describe the whole construction, so just mention that you have a PEPs, you can compute the radiation density matrix for a region, so the way this was done, I hope I wrote no. I didn't write the, yes, so the references are here, like it's from 2011, yeah, the one that gives this framework. The idea is that, so it's this one, CRB 2011, by Ignacio Firac and collaborators. So the idea is when you have a PEPs, so you assume that your ground state is given by a PEPs, for instance, or when you have some PEPs to say, you can compute the radiation density matrix for one part of the system. In this case, they looked at a geometry which was a cylinder, and they would trace out half of the system. Like you cut the cylinder in half, trace out part of the system. So what are you left with when you trace out part of the system? So tracing out means you contract together with itself, so with its bra, this part of the PEPs, right? So you do this kind of contraction. You can imagine that you are doing this thing here. Imagine that this is wrapped around the cylinder, and you do this contraction, and at the end you end up with something which looks like this. So you end up with a one-dimensional structure. And this is a very natural way of realizing this holographic connection, because it tells you that the degrees of freedom on which this equivalent or related one-dimensional theory lives are the virtual degrees of freedom. So this bond dimension. And yeah, I want to spend more time in here because this is a field on its own, where a lot of people are working now and exploring how local this one-dimensional theory is, depending on what the bulk theory was, for instance, if it was gapped or not, if it had topological properties or not. And it's a very rich field of investigation, I would say, where many people are working now, and I think it's one of the newer directions in which these tensor networks are also developing. Okay, I had a picture here, but it's the same thing I was mentioning today. Okay, and then I would like to explain a bit more about how to use these things in practice, because this is also the kind of work I do with these tensor networks. So as I said, there are these two lines or two ways of using these tensor networks, and one of them is like, okay, they are variational answers, say what can we do with them, which kind of things can we describe with them, which kind of physics, which kind of problems can we solve. And the other one is, okay, we have these local pieces to construct the many-body physics. And what can we construct with these pieces? What can we get if these pieces have these properties or these other properties? And so most of the things I mentioned so far are actually related to the formal properties, because it's really the basic building block also for knowing what you can do and what you can't. But I would also like to tell you more about how you use them in practice, right? If you have some problem and you have heard about matrix product states and tensor networks, and you are asking yourself, does this apply to my problem or not? What does it mean to use these techniques to solve one particular problem or one particular one? And before doing that, I still need to introduce another answer, so this will be very fast because I already sort of introduced it, which is the matrix product operator. So the matrix product operator was introduced in 2004. Simultaneously by Frank Verstraete and Juanjo García Ripoll and Ignacio, and by Michael Zvolak and Guifre Vidal. And it's a natural extension of matrix product states. So matrix product states, you can think of them as is a family of vectors in some vector space where the coefficients in a product basis have the form of a product of matrices. Right? So you take the vector space, you take a local basis, and then you just say, okay, I just look at vectors where the coefficients, each coefficient is a product of matrices. This is matrix product states. Well, you can do this in any vector space. It doesn't need to be the one of states in the vector space. It could be the one of operators, right? So for operators on our spin system, say, you can also construct a local basis, a product basis. This product basis could be given by, say, Pauli operators, for instance, a Pauli basis. And then this is just a matrix product state in this basis, right? This is a matrix product operator, actually. We can just write it in the spin basis by writing each of these operators in the spin basis, which is typically what we want to do if we are doing some numerics, right? If we want to apply this to our MPS, which was written in a spin basis. The way we picture that is typically, like I already did before, these shapes for the tensors with indices like like incoming indices and outgoing indices, right? Because our local basis now might have these two indices, IEA, for the IEA elements of the local basis. But we could also picture them as a simple MPS as we did before if we are using this basis, right? It will depend on what we are doing. So just matrix product operators and matrix product states. The simplest examples we can think of are operators which have exactly this form. And here I wrote an example. And I don't want to spend too much time because actually it's the example that I already showed before, right? So let me see if I just can explain it on the picture. So imagine that you have a very simple Hamiltonian, which is a local one, and it's just a sum of sigma x, right? This guy is the sum, actually, when we write this, we mean sigma x on the first side, tensor identity, 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 plus identity, tensor sigma x, tensor identity, identity, and so on, right? But we can also say, okay, this is the same as 1, 0, 0, 0, plus 0, 1, 1, 1, etc. If we just call 0 to the identity and 1 to the sigma x, which are two elements of the basis, right? Our basis will be larger. We will have also a 2, which might be sigma y, and a 3, which might be sigma z. But here we only need these two states to describe this thing, right? And actually, this thing is the same state that we described before as a matrix product state. We wrote this W state, and I told you that these were the tensors with the proper boundaries that I didn't rewrite here. These were the tensors that describe this state. So we can also use these tensors to describe this matrix product operator in the basis of Pauli operators, right? And if we just want, so the 0 would be identity, the 1 would be sigma x. And we will have all zeros for sigma y and sigma z because there is no component which contains this guy. And if we just want to write it with this picture with the two legs, right? We can just do. So if we have this guy, which would be the M alpha left right, with alpha going from 0 to 3 for the 4 Pauli operators, we can just change bases by acting with something local in here that goes from, okay, maybe I just do it like this, that for an alpha, right, gives you what are the IJ components. It's just a change of basis, right? Okay, change of basis meaning that we change the description of the NPO. And if we do this contraction, then we can just write this thing in this form that I was using before, that is IJ, but it's just the same thing, just in a different basis. Okay, we can also do nearest neighbor Hamiltonians, and in a very simple form. There is a systematic way actually of constructing them, and very easily we can do things that decay exponentially. What happens with things that decay algebraically, right? This is after all an MPS. But there is a trick that you can use, at least for finite planes, which is approximating anything that depends on the distance by a sum that is a sum of exponentials, right? Each sum of exponentials is very easy to write in this form, and then you can just use a finite sum to approximate to some precision whatever Hamiltonian you have. So in practice, you use this trick a lot. Okay, this also can be used to approximate time evolution, and when this was introduced, the idea was to describe mixed states, right? So as an answer for mixed states. So the Matrix-Planck states give you a description of pure states, but what if your state is, I mean, you are talking about an open system, or you want to describe a thermal state and so on. Then maybe you want to use these efficient ansatz also, right? So this is a good guess in some cases. Now, what is the difficulty? Well, the difficulty is that when you have an MPS, it is already giving you, if you are in this context of quantum mechanical system, it is already giving you a valid quantum state up to normalization, right? But normalizing is sort of a trivial thing, it's just a factor in front. This is not true with this anymore, right? Because to describe a mixed state, your operator, okay, okay. So your operator needs to fulfill some requirements, and these requirements are: it has to be Hermitian, it has to have trace 1, which is being normalized, and it has to be positive. Being Hermitian is sort of okay if you want to impose it in all the tensors, because you could choose tensors that are Hermitian themselves, or maybe better to construct the Hermitian part of whatever you have, right? Which will still be an efficient MPO-MPS thing. The tracing one, in principle, is easy because it's also a normalization, always if you don't have an operator which has trace 0. If you end up in an operator with trace 0, which might happen in practice, then this is not so trivial. But anyway, it's not the major problem. But being positive is really a nasty thing, because being positive is a property of the full spectrum. We don't know of any way of checking locally whether the MPO is positive or not. Actually, it has been proven that it is not possible. In general, if you are under some conditions, it is not possible actually. If you are given a tension and they ask you, okay, is this thing in the thermodynamic limit a valid MPO? This is undecidable. You don't know. And if it is just on a finite system, it is very hard to answer this question. So that's really not so nice situation. Which, again, in practice, it's not always so problematic, but in principle, it's a nasty thing. But there is a solution around that. And this is what we call often the purification form. So the purification, if we talk about purification, means that whenever you have a mixed state, right, you can always find a pure state on a linear system. So you have your system, you enlarge it with an ancillary system, which is at most as large as your system was, so the same dimension. And there is some pure state of the whole thing, such that when you trace out this ancillary system, you end up in the interesting state that you have. And this is a purification. So you can make an ansatz that tells you that this purification is an MPS. And it's an MPS with some structure. So for each site in your system, you introduce an ancillary system. Okay, maybe for the sake of the picture. So you have your system, right? And you wanted to end up with a description which was like this. Right? An MPO for your system. And okay, in this way, you don't know. But now we say, okay, for each side of my system, I introduce an ancillary one, which is the same dimension. So if this was D, this is always D. This is also D. And I do the same thing side by side, right? Okay, 3 sides of my system. And now I make an ansatz where, for this kind of decomposition, I have an MPS. This is my ansatz now. Instead of doing the ansatz directly for this, you can think my ansatz is for a purification of this form. And now I compute the tracing out of these guys. So I just draw here the adjoint of this. So this would be my psi system ancilla, and this would be my psi system ancilla, the bra. So I'm not writing again the complex conjugate. And now I trace out the ancillas. So tracing out the ancillas, as I said before, is connecting together the corresponding index, right? So I'm doing this, I'm doing this, I'm doing this, and of course I can just move the legs around so that they look a bit nicer. So I can just do it like this, okay? And like this. And of course, this is of this form, although not everybody of this form will be of this, in this shape. But if I would just take this thing together, this is an MPO. And it's a positive one, just by construction, because it just comes from tracing out something from a valid quantum state. So this is the purification ansatz. It's an MPO which has some structure inside. And we can work with this ansatz and use it in practice, or use it to here you have some of the relevant references that I mentioned before. So you can just use it for practical purposes, although it will get more costly, but people have tried these things in some problems. You can also reason about how efficient is this description, how is it connected to the other one. Like, it might be that this thing is positive. The problem is you won't be able to tell it unless you can diagonalize it completely. And this is exponentially costly in the system size. So in general, you won't know. But assuming that you have something that is positive, and you have it in this form, again, you also have a lot of freedom here, how you express this guy in tensors, right? So if this is positive, how easy it is to put it in this form? Is this form also simple if this one was? Well, it turns out it is not. Sometimes you have a very efficient form of this guy, of this category, but not of this one. So this one is very inefficient. So this was shown in this paper by Gemma de las Cuevas and collaborators. I think it's somehow something very interesting, but it also tells you that there might be efficient approximation. So it's again not hopeless in practice. And the other reference is the one I mentioned before that shows how difficult it is to know whether something is positive or not if it is in the NPO form. Anyway, so I mentioned this because it's actually pretty useful in practice for the algorithms. So if there are no questions about this, I will go to the part which is more practical about what kind of things can you do with this transaction. And okay. So all the explanation I developed here with MPSs, in principle, you can do basically the same things I'm telling about will be doable with PEPs at a higher cost and with this problem that the contractions have to be approximated. But if this approximation works, in principle, you can run the same algorithms, only they will be much more costly. So the kind of algorithms we have are basically to look for equilibrium states, which can be ground states, maybe low excited states, or can be thermal states also. But we also have algorithms to look for time evolution. Time evolution has a problem that I will mention, but in principle we have algorithms to work with it. And if we look at the algorithms themselves, there are basically two kinds of algorithms. One is variational. So we are trying to optimize some cost function. Typically, we are trying to optimize the energy to get a ground state. And the other one is how to apply a local operator on a tensor network or some shape. So typically, say a matrix product state. You have a matrix product state. You want to act on it with some relatively local operator. By local is not single site because that would be sort of trivial. But say two-side operator, in general, whenever you do something on more than one side, your bond dimension would increase. But you want to approximate the resulting state as a tensor network of the same one. So these are typically the two kinds of operations that we can do. So the first one I want to talk about is this variational ground state search. This is very important because it's actually what DMRG does. So you have heard of the DMRG algorithm. This is the state-of-the-art algorithm to solve one-dimensional problems, and actually is the one getting the most precise results also in some two-dimensional cases by using this kind of snake MPS. And the key for it being so successful is that at the end it's using an ansatz, which is an MPS, so it's looking for the ground state over the subset of matrix product state with some bond dimension, which is as high as the computational resources allow, so very high in this very competitive result. And as we already saw, there's very good reasons why the ground state is close to an MPS, or efficiently approximated by an MPS in many cases. So how does this work? So, of course, this is not the way the DMRG algorithm was originally explained, but it's like the simplest way to understand it once you are in this frame of mind of thinking of tensor networks. Okay? So the way to think of this is the following one. We want to minimize the energy to find the ground state. So that's just applying the variational principle. right? And in our case, what we want to do is to restrict the search over some family of MPSs with a given bond dimension. So our state is an MPS, as I have shown you already several times. We write it in this way. So if we just want to minimize this expression, that's also not very nice. All our variational parameters here are the tensors, okay? And this expression is complicated. Depends in a complicated way in terms of all the variational parameters, because there are products of all the components of the tensors, and then they are summed together. So it's not an easy expression to minimize directly. So we don't know what the minimum of this thing is. But the standard algorithm to that is what is called an alternating least squares scheme, which basically tells you, okay, let's fix all the tensors but one, and now minimize for this particular tensor. So if you do that, then if you write out this expression, all the a's are constant except for one. And this one will appear as complex conjugate here and without the complex conjugate there. And it will be contracted with the rest of everything. And the same thing will happen in the denominator, right? So if we do this graphically, we immediately see what we obtain. Because so the easiest way to explain it is assuming that the Hamiltonian itself is an NPO, which is the case whenever it's a nearest neighbor Hamiltonian, for instance, or in many other interesting cases. So our Hamiltonian is an NPO. Our state is an MPS, which looks like that. And we want to compute the expectation value of the Hamiltonian. So we put the Hamiltonian, and we contract with the bra, which is like that. So this is exactly the contraction. This is one contraction that we know we can do efficiently in the one-dimensional case. For the norm, we will have the same thing without the operators, just the contraction of the state with itself. Okay? Now, what happens when we say we fix all the tensors but one? Say that this is the tensor that we do not fix. So here is A, here is A adjoint or A dagger or whatever, depending on the notation. And here is A and A dagger. Okay? So everything except this tensor is what we need to compute. Like we can contract it all together, then write this thing as some big block here, which is contracted with A and A dagger. Right? This big block is not that big because this is only the bond dimension, and the physical dimension. Right? It's not. It doesn't depend on the system size. And this thing is what we call the effective Hamiltonian, because it's the Hamiltonian acting on just this side, taking into account all the environment of this side. And the same thing we can do in here, if we contract everything around this guy. Right? So actually it will look like that in this case, but this is very much because this is an MPS. So this will be A. And this thing here is what we'll call effective norm. And the expectation value is this divided by that, right, which is this divided by that. And this is what this expression means. So we just need to minimize this thing using A as our, so taking A as our variational parameters. And this is what is called a Ritz-Rayleigh quotient. So the minimum of this thing is actually the solution of a generalized eigenvalue problem that I hope I wrote somewhere just here. So we just need to solve this generalized eigenvalue problem. You can just see it by taking the derivative with respect to each element of the A and making it equal to 0. Then the solution is the minimum eigenvalue for which is true. There are standard algorithms, numerical algorithms to solve this problem. So in principle, you can just do this. You don't do that in practice because this is not the most efficient alternative, but conceptually this is enough. So the cost of this is going to be the cost of these contractions, but you can compute them and they can go like d to the cube, which is very nice. So it will be, of course, everything will be polynomial in the number of sides because you have to go over all these many sides with the contraction. Say d to the cube. This effective Hamiltonian or this effective norm, but here is the effective Hamiltonian, the only thing that matters. It lives in on this space, which is small d times capital D squared. So the Hamiltonian itself is already d to the 4. So the dominant cost in here will be computing this Hamiltonian and doing operations with it, which is d to the 4, at least. It can be do better than that. So it can be done better than that with some optimization, which is just using the structure of the Hamiltonian itself. I'm not describing how. But then at the end, the cost can be reduced to d to the cube. So what you do is you solve this local problem for this A, you change this A, and then you do the same thing for the next one. And you do this for all of them, and then go back and continue doing the same thing until your energy has converged. A very nice thing of this problem is that because you can compute the exact minimum at every step, and you already have one tensor that you had in the step before, your energy can only go down. It can never increase, because it won't increase. It will just stay the same thing by just keeping the same tensor. You are going to the minimum of this local equation. So it's always going down, and because the energy is lower bounded, of course it cannot go down to infinity. At some point it will converge. Of course you don't have a guarantee that it will converge to the true solution. It can get trapped in a local minimum, but it will converge, which is a very nice property of an algorithm. It also doesn't tell you anything about how fast it will converge. It can converge very slowly because it will be doing very small changes in its sensor every time. Okay, just to mention that this is the basic idea. It can be optimized by using the structural tensor, by using the canonical form and so on. But then the basic idea is just what I said. And this is actually the DMRD algorithm, the basic ingredients of the DMRD algorithm. It's an algorithm that you can implement in its basic form in just a short time, and then you can just use it for much larger systems and do exact harmonization. So it's very successful. So another thing that we need to do often, we have to do it for contractions of pairs, as I mentioned before, and we have to do it if we want to do time evolution. Is this approximating an operator, for instance, an MPO? So it can be some 2-side gate, but let's think it's an MPO, acting on, say, an NPS, and finding an NPS again. So what happens here is that if we have an NPS and we want to apply an MPO on it, we can just take the contraction of these things together, exactly, right? And then you will have an NPS. But what is the dimension of the new NPS? Well, in general, it will be the product of these two dimensions. So if we do this many times, of course, this is not efficient. Or if we are already at the largest bit that our computer can handle, we cannot do that anymore. So a very interesting operation is to, say, return this thing back to the form of an NPS with a maximum bond dimension. Like finding the best approximation by the NPS that we want or can handle in our computer. And this can be done in two ways. One of them is what we would call a local truncation, which is the same thing as I explained before to find the NPS description of a generic state. You go over the whole chain and do the singular value decomposition, but you just keep, instead of keeping all of them, you just keep a maximum number. This is what we would call a local truncation, but there is another way, which is also variational, which consists, and it's more exact, on minimizing the distance between the operator on your initial state and the resulting state. And this can be done by a variational algorithm which in structure looks very similar to what I described before, only you don't have to solve an eigenvalue problem, but just have to solve a set of linear equations, and actually by using the canonical form this can even be better. And this in principle can get you a better approximation because you are allowing your MPS to explore all the family of MPSs and not just doing one local truncation one by one. If the operator is not an MPO, but is just a... Oh, this is how it's sinking. So if it is not an MPO, but it's like something like a two-body gate, and this is a key ingredient if you want to do time evolution with DVD, I will mention this in a moment, then you can do both things, right? So you can just say, okay, I have my MPS. I apply a two-body gate because I'm simulating some quantum circuit or because I'm simulating some evolution or whatever. Then I can say, okay, this only acts on these two tensors, So I can just contract and then truncate to return it to the MPS form. This is what I would call a local truncation, but you can also say, okay, I allow all my tensors to move to approximate this thing better. It's not very important. It's just that you have different alternatives to do things, and using this MPO MPS structure, you basically can do any of them, and you can have all these pieces sort of in your toolbox, and then use them to do a lot of calculations using this answer set. So, what if you want to do time evolution? Okay, so the simplest scheme to do time evolution is a time evolving block decimation algorithm, so TEBD, which was introduced by Geoffrey Vidal in 2003. And the idea is, okay, you have to do the evolution with some Hamiltonian. So the evolution, even if your Hamiltonian is local, so the evolution looks like the exponential of the Hamiltonian. The Hamiltonian might be a nearest neighbor Hamiltonian, or even if it is a local one. The exponential contains all powers of the Hamiltonian, so it's non-local at all in general. It will contain terms like with this guy together with this guy, product with this guy, and so on. And all of them. So it's a very non-local operator. It's something that looks like this in this tensor representation, right? And it doesn't have a clear, easy, nice tensor network structure. But you can approximate it as small steps of evolution, like thinner slides, like this, so on, where each of them is some delta of the Hamiltonian. And now each of these steps you can break down into smaller things. So typically you could just use some MPO approximation of each of them, and so on. So this is an approximation now, but it's sort of a good approximation in the sense that by making these steps smaller, it gets better and better. So one thing that I didn't mention before, but it's important, is that whenever you truncate the effect of one MPO on your MPS, so whenever you do this kind of thing, there is some error, right? Because you don't have the exact vector anymore. You have an approximated one. This error is called the truncation error. When you do this thing, there is also an error, which is called the Trotter error, because this typically uses a Suzuki-Trotter decomposition, and is governed by however small you do this step. This error is sort of a benign one, because you can control it easily by changing the step or changing the way you break down this evolution. And okay, here I just pictured the simplest example, which would be if you have a nearest neighbor Hamiltonian, you can say, okay, I can split my Hamiltonian in terms which act on even odd or odd even, okay? And all the even odd terms, they do not overlap, so they are like this. So they commute with each other because they do not overlap, so the exponential of the even terms is the product of exponentials, and the same thing for the odd. So you can just approximate the exponential of this sum as the product of the exponentials. And then you will be doing some error, but if the delta is small, this error will be small. And of course you can do something a bit more refined by using another expansion. So this is the most used one. And then you can just do the operation that I described before, that you act with each of these individual exponentials on two sides and return to the MPS form by truncating, or you just say, I apply the corresponding to the even or to the corresponding to the odd, and I do a global truncation by minimizing this distance. There is not a big difference. I mean, typically the errors get smaller if you do the global optimization, but it's also more costly. But anyway, you can just do this for as many steps as you require to reach the desired time. You can do this for imaginary time evolution, meaning that instead of the real unitary exponential, you use a real tau instead of the IT. And this tau is like the imaginary time. It corresponds to imaginary time. It corresponds to t being imaginary, right? And the idea of imaginary time evolution is like a projection, a progressive projection onto the ground state. So you start on any arbitrary state. This doesn't depend on tensor networks. It's not a technique of tensor networks. Actually, it's used in other fields. It's used, for instance, in lattice QCD. Okay, and the idea is very simple. You take an arbitrary state, you decompose it in the eigenbases of the Hamiltonian. So it has some component in its eigenvalue. Now you apply an exponential of the Hamiltonian. Of course, if you put it in that basis, then it's easy to see that each term will evolve with an exponential which goes with the corresponding eigenvalue. So when the tau gets very large, these terms are suppressed exponentially. If you are normalizing after every step, you will have the terms decay exponentially, but at different rates, because the rate is given by the energy. And actually, if you are normalizing, it will actually be given by the difference to the energy to the lowest one. And if you continue evolving for a very, very, very large time, all of them will disappear except for the first one, because you are normalizing. Otherwise, of course, everything in norm disappears. So at the end, if your initial state had some overlap with the ground state, you end up on something which is proportional to the ground state. Unless it is degenerate, of course. If it is degenerate, then there will be some other term which also doesn't decay. And this strategy is what is called imaginary time evolution. And it has some advantages. So it can be used to search for the ground state. It is actually the thing that one uses in the two-dimensional case, although the variational strategy that I described before for the ground state is also possible. It has some inconvenience in practice. And people typically use this imaginary time evolution. And it has some advantage. For instance, if you start on a state which is orthogonal to your ground state, you won't end up in the ground state. You will end up in the lowest, in the state with the lowest energy that has some component in that. And you can use that, for instance, to target different sectors, for instance, with a different total spin or something like that. And actually, it's like the main strategy this thing is used for in the context of lattice QCD. The problem of doing this with tensor networks and this TBD kind of decomposition is that to do this Trotter decomposition, you really need that the Hamiltonian is short range. Even if the Hamiltonian has a nice expression as an MPO, doing TBD like that doesn't really work. But there are other strategies that one can use to also approximate exponential. So it's a difficulty, but it's not like a no-go. Real-time evolution, of course, I mean, you can do exactly the same thing I described before with a real unitary evolution operator. What is the problem? The problem then is physics, right? So that everything I told you before about MPSs and so on was that the ground state of local Hamiltonians is well approximated by various product states. Even if it is critical, well, it still works. Actually, in many cases with long ranges, it also works, and you do it in practice and no problem. What happens with time evolution? It can be that the thing is absolutely not an MPS at all after some time. And so there is some formal mathematical results about that. In free fermionic models, but there is a very intuitive picture that one can draw to understand what's going on there. So the idea of these models is you have so the diagonal modes of the Hamiltonian that do not interact with each other, right? So you start on some state, which is not a ground state of the Hamiltonian or an eigenstate. Of course, if you start on a ground state or an eigenstate of the Hamiltonian, nothing evolves, no problem. But you start on something which is not an eigenstate of the Hamiltonian and then switch on the Hamiltonian. This is what is called a global quench, because you switch on the Hamiltonian everywhere. So excitations will be created everywhere because you are not in the ground state of your Hamiltonian or close to it or anything. So the thing will evolve. You will see some dynamics, right? And actually, it's a very interesting problem because it contains a lot of very interesting physics in many cases. But what can be happening here? So imagine, I will do the picture again. Imagine that your state, so this is a toy model for what might be going on in there. It's a very simple toy model, but it's quite close to what might happen in one of these free fermionic Hamiltonians. So initially you are in a product state. So you have an MPS, which is one dimension 1. Because you just started on a product state. It's the ground state of some different Hamiltonian, but this is not the issue here. It's not the ground state of the Hamiltonian you have. So when you switch on the Hamiltonian, you actually have some excitations in your state, because your state is not the ground state of the Hamiltonian that you have. So a very simple picture would be that you switch on your Hamiltonian, and the kind of thing you have is sort of maximally entangled pairs, but they are localized, right? So they are, on every side you have a maximally entangled pair. And they propagate freely. It means that in time they will just fly away and they will cross with each other but won't see each other, right? So they will just go away. So at the beginning, say that these are your sides. If you just cut your system in two, there's no entanglement between this part or this part. This is a product state, maybe it's product state with one dimension 1, whatever. Now imagine that this evolution is just moving things away, so they are just flying away, right? So this thing is going in that direction, and this thing is going in that direction, and so on, right? And they go, this is a very simple model, they all go with the same velocity, while in a real model you will have excitations which travel, so the eigenmodes will have different velocities, probably, and so on. But this is a very simple model, which can already, well, this doesn't look like the same velocity, but anyway. So sometime away, like say here, at this cut in time, so time goes in this direction, you can see that this pair which was here is now there, this pair which was here is now there, and this pair which was here is now wherever, and so on, right? So if you do the same cut, or a different one, say you cut here, yeah, you now have to cut a certain number of maximally entangled pairs. And this is what tells you how much entanglement you have between one part of the other, the number of maximally entangled pairs you have to cut. And if you do this in steps, and one way of doing that is doing a tensor network model for this evolution, which would be, okay, on every time step, they just move one side left or one side right, depending on whether they are traveling left or right. If you do this thing a bit more precisely, you will see that the number grows linearly with the time. And if the number grows linearly with the time, the entropy grows linearly with the time, the one dimension grows exponentially with the time. And this is basically a no-go. If you want to describe a state that has this amount of entanglement, you need a one dimension that grows exponentially with time. And of course, in practice, you cannot work with a one dimension that works exponentially with time. So what happens in practice is that you can do the real-time evolution, as I described it, for short times. And for short times, it will work. And you might still get useful physical information of something that happens at short times. But you can also work with situations when you don't have this huge growth of entanglement. This is like a limited case, and in global quenches it's the case often. But you can have just a local quench. You can have something which is the ground state of your Hamiltonian, say, and then you flip one spin in the middle, or you change a coupling in the middle, or you change the magnetic field on one side. And then, of course, there will be excitations created, but basically, they will be created just on one side and propagate just from one side, and you won't have this huge growth of entanglement. You have a smaller one, and you will still be able to cope with that, with your one dimension. And of course, it can be that you are not in such a non-equilibrium situation. If you are closer to equilibrium, you can still do things. And closer to equilibrium, for instance, can be, you might be trying to describe an adiabatic process. So you start from some ground state and start evolving. And you might still have problems, but you won't have this problem in general. So this doesn't mean that you cannot do time evolution, but it means that time evolution, real-time evolution, has very serious limitations if you want to do matrix product state calculations. There are other algorithms for doing time evolution, and so maybe I just go over it. So they are basically going around the difficulty with long-range interactions. So they can improve on the precision and so on, but mainly I would say probably the biggest inconvenience of doing TEBD-like is that you can only work with short-range interactions, and the moment your interactions get to next to nearest neighbor, it gets much, much more complicated. Well, there are other algorithms that use more the structure of the Hamiltonian itself as an NPO, and some of them were explored by Juanjo García-Ripoll in 2006, and one of the most successful one, which is used often, I would say, is this Arnoldi approximation of the exponential, which means at the end, the idea is just to approximate the exponential in a different way. So still for the smaller steps, but instead of doing this trotterization, which as I said has a problem if the interactions are long range, you use powers of the Hamiltonian expressed in a reduced basis. And so powers of the Hamiltonian are still okay. The Hamiltonian itself can be an NPO. The powers of the Hamiltonian will be like a tower of NPOs. But if you just have a few of them, you're still okay. And you can still do these approximations. And these Arnoldi methods, what they do is to construct a reduced basis, which in this case is made out of MPSs. And and compute the Hamiltonian or the function of some matrix in this subspace, and then construct an approximation to the full result. So this can be done all in the context of matrix product sets. And then a more recent approach is what is called the time-dependent variational principle, which was proposed by Yuto Hegeman and collaborators in 2011. And it's also a nice idea because the idea there is, okay, you have your MPS, which has some one dimension. Whenever you do evolution, it goes out of the set of MPSs with a given one dimension. And what we typically do is we do the evolution and then project back to this subspace because we truncate. So we say we apply a small step of evolution, we approximate. This is truncation. Their proposal was, okay, what if we just write the tensors themselves as time-dependent, and we try to calculate the trajectory directly on the set of matrix product sets. This is the main idea. Well, you can just write an equation for the derivatives of the tensors. They originally proposed it for translational invariant systems. It was later done for non-translational invariant, so open boundary conditions by Luca Tagliacozzo and other people. And then very recently, they had also a new formulation of this thing, which simplifies it a lot, which makes it very similar to the variational method again, and it works for non-translational invariant. And at the end, I don't want to give the details, but the idea is that this sheet here represents the MPSs with has some curvature. We don't know what the geometry, well, he knows quite well, Yuto Hegeman, the geometry of this set. But the idea is that it has some curvature, right? And your MPS, when you do time evolution, it will move in there, and you can just compute the tangent space to this curved surface, and do this all in a closed form using the tensors of your MPS and the freedom of your gauge. And actually solve the equations and see how you have to change your tensor to approximate this evolution. And this can be done also in a very similar way to the variational algorithm. And it can also work with long-range interactions. And okay, one last thing I want to mention is that we can use these things also to compute thermal equilibrium states. And this is also a very used algorithm, which works very well because I skipped this form, but there are formal results that tell you also that thermal states of local Hamiltonians are very well approximated by PEPs. So this is not even only for the one-dimensional case. How do you compute thermal states? Well, the one-dimensional picture is that your thermal state gives ensemble is just the exponential of the Hamiltonian with some real coefficient, which is the inverse temperature. But this looks very much like imaginary time evolution acting on an operator, which is the identity. We just split it in two parts. I mean, we could also like say it's an operator acting on the identity. The identity is a very nice MPO because the identity on an n-side system is the product of identities on each side, right? So the identity, I told you before, is an operator like this. So for an n-side system, it's just something like that. Okay, it's just a product of this thing, it's an MPO with one dimension 1. And if you want to do imaginary evolution, you can use the trick that I described before. You approximate the small steps of the exponential and act, in this case, on both sides, because this is an MPO. There is something that I'm like completely ignoring here, which is that we know very well how to minimize the distance between two MPSs, which are vectors. So we minimize the Euclidean distance. This is an operator. So we want now to approximate this thing as an MPO, which looks like that, right? But we don't have good ways of minimizing the trace distance, for instance, between two operators, which is what we would like to. Because at the end, when we are trying to approximate mixed states, what we want is the expectation values of local operators are very similar. And for this, we would need to minimize trace distance. We cannot do that, so the trick that we always use is to vectorize this thing, treat it as an MPS, which lives in a converge. So if the distance is 0, that's no problem, because both of them are norms. But of course, it might not be the best thing if you are not right there. But okay, it's not a problem for thermal states, which converge very well, and which are well approximated by these guys. So we just do this, iterate as for time evolution, and find an approximation to the terminal state. And here we actually go around the positivity problem very easily, because almost for free you get a purification ansatz. Because of course, if your thermal state is e to the minus beta h, you can always write it as the product of e to the minus beta half h times itself. Or the adjoint of this guy times itself, because if it is exact, all of them are the same, right? So the adjoint and itself. And then this thing, if I have an MPO approximation for this guy, this thing is already a purification, which will be a good approximation to this guy. And then you have like the problem of the non-positivity solved. Okay, there is an alternative algorithm proposed more recently by Steve White to approximate thermal states by sampling over several MPSs. And I'm already stopping, so I just mentioned that there is another algorithm for contraction of MPSs, which is this tensor renormalization group. There are several flavors of this already. This was developed also in more recent years. And it defines a new strategy to contract a tensor. Maybe I just show you the picture, that's a good thing. So it can be used, for instance, in a two-dimensional network. If you want to find a contraction, instead of going from the boundary towards the inside, you can just say, okay, I take several tensors and group them together and define a smaller tensor from that by truncating somehow the degrees of freedom of the boundary. This can be done in different ways, and is what is called tensor renormalization group in general. And it has been used, for instance, to contract partition functions of 2D models, where the partition function is 3D, for instance, and you can contract a three-dimensional tensor network. And and this has been done basically for classical models, as far as I know, that you have good results. And well, you can then compute correlations or physical quantities of the model in this way. Okay, there are different ways of doing this, and there are recent proposals how to improve it. And I think I'm just stopping here. So the things that I haven't mentioned are, for instance, other kind of tensor networks, like meras. They are quite different from matrix product states. In 2D they are actually a subfamily of pairs, but they introduce an additional dimension. So you have a one-dimensional system, but then you have an extra dimension for your tensor network. So your tensor network has sort of a tree structure which gets more complicated and is not a tree anymore. So if you think of constructing a tensor network for a one-dimensional system which does not have this linear structure, but it looks like a tree, of course you can do that. Well, this gives you some power. It contains some different kind of correlations and more entanglement. But you can define a more complicated scheme to define such a network by introducing some additional tensors. And this is what the mera does. I'm not showing you the mera here, but it's also a very active field now, especially because it has been pointed out that mera could actually realize a discrete version of this ABS-CFT correspondence. Like there is a boundary, and there is a bulk, and there is this dimension which can be interpreted as a renormalization dimension. So there are many people looking at this now, and whether with these tensor network tools one can learn something more about these theories. And another direction that I haven't touched at all is that of symmetry. So symmetries, of course, are very important. If you are studying some physical problem, the first thing you look at is which symmetries it has. So you can also look at symmetries in tensor network. So what you can do is to define tensors which have the invariance under the symmetry, and then guarantee that your state is invariant. In the case of matrix product states and PEPs, because their formal properties are better understood, it is actually known that if you have a state which is symmetric, under some conditions, the tensor, or it has to have a representation with tensors which have the symmetry. So it's very obvious that if your tensor has a symmetry, then the full state inherits it. But to go the other way around is not trivial, but under some conditions can be done. And this has a lot of applications, so the symmetries. If you have tensors which have the symmetry, You can use them in algorithms, so you can reduce the number of variational parameters because you know that the tensor will only have some components which are free, and actually will have some form that might be restricted by the symmetry. And you can also use it in this more analytical perspective where you construct states which have tensors, which have some symmetries. And by changing these symmetries, you can actually construct a lot of states which have different properties. You can construct states with topological properties. You can actually do gate symmetries, so local gate symmetries. You can construct states that have Bañuls excitations. You can even construct chiral states. And it's also a very, very active field of research, which is much more formal. And I think I basically stop here. Well, if you have any questions, please go ahead. No questions?
Just one. So with the thermal evolution,
Yes.
is that in any way equivalent to using sort of like a compound real and imaginary time? So like 1 plus I gamma? Because if you run like a numeric system with 1 plus I gamma, you get some damping, so it kind of damps, but you also get real-time evolution.
That's different. So you can do different things. Of course, you could do that with this script, and it would be just doing exactly the same thing that you would be doing with any other method, but within the framework of tensor networks. But you can just compute an approximation to your thermal state, and then do real-time evolution of that. Like, for instance, to compute time-dependent correlations. Like, you do some operator, you wait. This has been done also. There are different ways to construct this. It has a tensor network structure, and then you can use these techniques to compute it.
If there are no other questions or comments, let's thank both speakers again.